Hi, so in this video I'm going to derive the viscosity of a gas. So let's say we have a so we have, this is our axis basically. Our z axis running up here and our x axis running along there. And we're going to say we're going to have some sort of velocity distribution going in that way. So ux here, that's the mean velocity in the x direction, is going to be different from ux up here. So we're gonna, to work out the viscosity, we're gonna use the relationship that the momentum flux of the x component of the momentum in the z direction is equal to minus the viscosity times by the partial derivative of ux by dz. So we're going to use this relationship. We're going to find this momentum flux, and then from that we can work out the viscosity. The derivation I'm going to show you is only approximate, but it's the standard approximate derivation. So let's say we take a particle here, and it's going to travel this distance dz across the plane, like that, and we're going to say it's traveling at an angle theta. So the momentum this particle carries is going to be p, let's call it p1, equals m times by ux, or rather the momentum in the x direction, which is a function of z. So ux is a function of z, and this is the momentum it's going to carry across that boundary. We can say for every particle that goes this way across the boundary at this angle, we have a particle that goes this way across the boundary, like that, at the same angle, on average. The momentum of that top particle is given by mux z plus dz. So the net contribution for both of these particles crossing the boundary is going to be mux times by z minus dz minus mux z plus dz. Notice that I've taken this term to be second. That's because we're taking the particles going up to be positive. And if we Taylor expand that, we get ux z plus partial derivative of ux with respect to z times by dz minus the partial derivative, plus some other terms that we're going to ignore. Ux plus ux dz, and that gets us minus 2m dux dz. So we now need to work out what dz is. So this was dz here, and this length here is on average, or going to be the mean free path length. Mean free path. I know I do my lambdas really weirdly, sorry. So this is on the scale of a mean free path. We're only doing approximation, so the exact coefficient doesn't matter. I think on average it is actually 2/3 the free mean path, but we're just going to stick with this quantity here. So we can write that then as minus 2m dux dz times by the mean free path times by cos theta, because that z is the cosine of this length here. Okay, so then the momentum flux for that surface is going to be the momentum taken times by the particle flux. So the particle flux, which is the number of particles per unit area per unit time, is given by F is given by Vz, the velocity in the z direction, times by F of Vz, or actually F of V, times by d free V. And we can write that in plane polar coordinates as V of Z, F of V times by phi squared. We'll write that in polar coordinates as well. So we get phi cubed cos theta sine theta d theta d phi d phi. And if we then also write this as, so this is kind of like the velocity distribution, it's not the speed distribution, and the speed distribution is related to the velocity distribution like this, 4 pi. So if we write that in terms of the speed distribution, our momentum flux becomes okay. From that we can work out our momentum density up here using this expression up here for our change in momentum. I'll zoom out a bit so we can see. Okay, so momentum density is equal to, and one of these twos cancels, so we get minus 1 over 2 pi. We can take this and this outside of the integral, just because we can assume they're constant. Basically, we can assume we have a linear distribution of ux, and then we have the integral of 0 to infinity of d phi, and we're integrating the part derivative, this speed distribution times by phi squared. That's, oh no, sorry, just phi. Yeah, we always have a mean phi path here. Okay, and then we integrate from 0 to pi by 2 times by cos squared theta. We get a cos from up here, and this one down here, sine theta d theta, and 2 pi 0 d phi. Okay, so in some cases when I've seen this derivation, they have had a pi here instead of pi by 2. The reason for that is they haven't used this as a change of momentum, they've used a different quantity. I just think this one's slightly more intuitive. So the reason we're only doing pi over 2 is because we only need to take account of the particles traveling this way. So the particles traveling this way, because we've already taken account of the particles going this way without changing momentum. We've taken account of the distribution there. So that's why we're only doing pi by 2. And I know that can be quite a confusing topic. So if we then do mean free path over 2 pi dux dz, this here is the average speed, and if we integrate this we are going to get, let's do this, we get 1 over 3 minus 1 over 3 cos cubed theta pi over 2 times by 0, and then there we get 2 pi. So you're going to cancel with you, and then you're going to get us 1 over 3. So we get equals the momentum flux is equal to minus m times by mean free path over 3 times by the average speed times by ux dz. And comparing that with this expression up here, we can see that we have this as our viscosity. So that is our viscosity. However, this coefficient, this free coefficient, 1 over 3 coefficient rather, totally depends on the assumptions we've made. So we're probably best saying that the viscosity is equal to some constant, call it A, m times by the mean free path times by phi, where this constant just totally depends on the assumptions made during this derivation. So like for example, we used the mean free path as a scale here when you could use 2 over 3, etc. To get the exact coefficient you would have to do a very long derivation. So that's this video. Thanks for